Hello everyone, welcome back. I'm your friend Inside. So today we're going to learn the next section of the Algebra 2. They call it modeling. The word model can actually have a lot of meaning across different domains in this word. So which one he was talking about is unknown to us. So let's get into it.
If he is building a tree tower, which is a tower built on top of a tree. The tree is currently 5 meters tall, and if he has found it, I don't know if iffy or ify, and if he has found it is growing by 0.1 meters a month, or a tenth of a meter a month. The tower is currently 2 meters tall, so this tower that sits on top of the tree is 2 meters tall currently, and iffy or ify adds to it at about 0.2 meters a month. So I guess he or she, I don't know iffy, well, let's just say he, is continuously building this tower on this continuously growing tree, which is fascinating. All right. The function a of m returns the tree's height in meters m months from now. Fascinating. The function b of m returns the tower's height in meters m months from now. So this is the tree's height. A of m is the tree's height. B of m is the tower's height. Find the formula of the two functions. So a of m, so they tell us the tree is currently 5 meters tall. So it's going to be 5 meters tall right at the start. And then every month it is growing by 0.1 meters. So it's going to be 5 plus 0.1 times m. And this m here, this is not meters, this is actually the months. Remember, m is the number of months. So after 0 months, which is right now, where this is just going to be 5. After 1 month, it's going to be 5.1. After 2 months, it's going to be 5.2, which is exactly what we want. All right, now let's think about the tower. So the formula for b of m. So the tower is currently 2 meters tall. It's currently 2 meters tall, and it grows at 2/10 of a meter per month. So 2/10 times the number of months. And once again, this m right over here is not meters. I'm not writing the units here. We're just assuming that whatever this returns is in meters. This m right over here is the number of months that pass by, the number of months from now. All right. The function c of m returns the vertical distance between the ground and the top end of the tower. Makes sense? That would be from the bottom of the tree to the top of the tower. Write the formula c of m in terms of a of m and b of m. Well, the total height is going to be the height of the tree, which is a of m, plus the height of the tower, plus b of m, plus b of m. That's what c of m is going to be. And then they say write the formula of c of m in terms of m. Well, we just need to add these two functions. So if we add 5 plus 0.1m to 2 plus 0.2m, that's going to be, let's see, we could add 5 plus 2, and we're going to get 7 plus, and if I have 0.1m and I add another 0.2m, that's going to be 0.3m, 0.3m. And we are done. We got it right.
Alright, so according to this video, what he told us is that the modeling for an function, the modeling for the problem is, in other words, try to find a function that perfectly describes the problem. Or in a more simplest way to describe that would be try to use the mathematic formula to represent the real-world problem, or try to use the math to solve real-world problem, or try to use the math to, yeah, that's exactly right, try to use the math to solve problems, especially real-world problem. The second one is interpreting features of functions.
Interpreting features of functions.
Interpreting features of functions. What is that?
We're told Divya is seated on a Ferris wheel at time t equals 0. The graph below shows her height h in meters t seconds after the ride starts. So at time equals 0, she is, looks like about 2, what is this? This would be 1.5. So it looks like she's about 2 meters off the ground. And then as time increases, she gets as high as, it looks like this is close to 30, maybe 34 meters, and then she comes back down, back to, looks like 2 meters, and up to 34 meters again. So let's read the question. So the question asks us, approximately how long does it take Divya to complete 1 revolution on the Ferris wheel? All right, so this is interesting. So this is when she's at the bottom of the Ferris wheel. So then she gets to the top of the Ferris wheel, and then she keeps rotating until she gets back to the bottom of the Ferris wheel again. So it took her 60, and t is in terms of seconds. So it took her 60 seconds to go from the bottom to the bottom again. In another 60 seconds, she would have completed another revolution. And so, let me fill that in. It is going to take her 60 seconds. 60 seconds, and we of course can check our answer if we like. Let's do another one of these. So here we have a doctor observes the electrical activity of Finn's heart over a period of time. The electrical activity of Finn's heart is cyclical, as we hope it would be, and peaks every 0.9 seconds. Which of the following graphs could model the situation if T stands for time in seconds and E stands for the electrical activity of Finn's heart in volts? Well, over here it looks like we peaked at 0 seconds, and then here we're peaking a little bit more than 1. This looks like maybe at 1.1, now maybe at 2.2 and 3.3. This looks like it's peaking a little bit more than every 1 second, so like maybe every 1.1 seconds, not every 0.9 seconds. So I'd rule out A. This one is peaking, it looks like the interval between peaks is less than a second, but it looks like a good bit less than a second. It looks like maybe every 3/4 of a second, or maybe every 4/5 of a second. Not quite 9/10. 9/10, this first peak would be a little bit closer to 1, but this one is close. Choice C is looking good. The first, we're at 0, then the first peak, this looks pretty close to 1, but it's less than 1. It looks like a 1/10 less than 1. So I like choice C. Now choice D, it looks like we're peaking every half second, so it's definitely not that. So this looks like a peak of every 0.9 seconds. This is the best representation that I can think of. And you can actually verify that. If you have a peak every 0.9 seconds, you're going to have 4 peaks in 3.6 seconds. So 1, 2, 3, 4. This looks like it's at 3.6. Over here, you have 1, 2, 3, 4. You've had 4 peaks in less than 3 seconds. So this one definitely isn't 0.9. So instead of just even forcing yourself to eyeball just between this peak and that peak, you can say, well, if we're every 0.9 seconds, how long would 3 peaks take, or 4 peaks? And then you can actually get a little bit more precise as you try to eyeball it. So we can check our answer and verify that we got it right.
Sorry, what is this? What is this kind of video told us? I don't know.
A little bit more than 1. This looks like maybe.
Okay, so at the beginning, what it showed us is a graph with repeated periods inside of that. Then it asks a question: which of the following graphs could model the situation if T stands for time in second and E stands for the stands for the electrical activity of Finn's heart in volts. This is another problem. The problem is a doctor observes the electronical activity of Finn's heart over what? Over a period of time. The electronic activity of Finn's heart is cyclic and peaks every 0.9 seconds. Then we're going to do a choose. We're going to try to find one that would repeat itself for every 0.9 second. I guess that's a method for solving this problem. And it shouldn't be that hard, as we could say the A would definitely be the answer.
Now choice D, it looks like we're peaking every half second, so it's definitely not that. So this looks like a peak of every 0.9 seconds. This is the best representation.
Wait, oh, I got it. If we choose the A, it's greater than 1 if you look at it carefully. But if we choose the C, it would be less than 1 second, which is 0.9 second.
A barista poured a cup of coffee. The initial temperature of the coffee was 90 degrees Celsius. At time t increased, as time t increased, the temperature C of the coffee began to decrease exponentially and approach room temperature of 20 degrees Celsius. Which of the following graphs could model this relationship? So we're starting at 90 degrees Celsius. It looks like all of the graphs start at 90 degrees Celsius at t equals 0. And we're going to approach the room temperature of 20 degrees Celsius. So this first one does approach the room temperature of 20 degrees Celsius as T increases. Now this one, when T is 70, I'm assuming this is in minutes, when T is 70, it looks like it has the temperature going to 0 degrees Celsius. So that cup of coffee is going to start freezing. So I think I could rule out B. Also, this looks like a linear model, not an exponential one. C, it does get us to this end state that stays at 20 degrees, but it doesn't look like an exponential model. It looks like it's linearly decreasing, and then it stops linearly decreasing after 50 minutes, and then it just stays constant at that temperature of 20 degrees. So even though it gets us to the right place, it does not look like an exponential decay. So I would rule choice C out as well. So A is looking good. D, we are starting at 90. It does look like an exponential function. We have exponential decay right over here. We are approaching something, but it's not the room temperature of 20 degrees Celsius. We're approaching 30 degrees Celsius here. So I'd also rule out D. So A is looking good. It's an exponential. It's decreasing exponentially, starting at 90 degrees Celsius, and it's approaching the room temperature of 20 degrees Celsius. Let's do another one of these. So it says, let me scroll up a little bit. So it says, after the closing of the mills, the population of the town starts decreasing exponentially. The graph below represents the population P in thousands of the town T years after the closing of the mill. All right, so it looks like the population starts at 40,000. It's decreasing exponentially. It looks like over time the population is approaching 20,000 people. So what is the question here? Based on the graph, with the mill closed, what does the population of the town approach as time increases? Well, we just said it. As time increases, it looks like it's coming close to, it's approaching 20,000. It's approaching 20,000. It's already gotten below 22,000 as far as, it looks like after 20 or 22 years, we've already gotten below 22,000. So we're definitely below 30 or 40,000, but we haven't gotten below 20,000, but we are approaching it. We could even check our answer if we like.
Alright, if you look at those titles for each video, you see the first one they call it periodicity of algebraic models, and the second one it's called end behavior of algebraic models. And for each title, it indeed indicates what he was trying to say. Okay, third one is symmetry of algebraic models.
Sid is experimenting with a piece of sandpaper and some wood. He tries scraping the piece of sandpaper over the wood in different ways to see how much is scraped off. The thickness of wood scraped off in millimeters as a function of the speed of the sandpaper in meters per second, T of V. So this is the thickness scraped off. So that's how much, so that's the thickness, or how much is scraped off. And it is a function of speed. And actually, since they're using V, and also they're getting negative values, so we care about the direction. I'll even call that, it's actually the velocity. So this is how much is scraped off as a function of velocity. It's shown below. And so if the velocity is greater than 0, that means that the sandpaper is moving to the right. That makes sense. That's a standard convention. And if the velocity is less than 0, means the sandpaper is moving to the left. Fair enough. The function is even. What is the significance of the evenness of this function? Well, the fact that it's even means that T of V is equal to T of negative V. So that tells us that if our velocity is 8 meters per second to the left, we're going to get as much scraped off as if we go 8 millimeters per second to the right. And we see that right over here. So that is equal to that. If we go at 6 meters per second to the left, we're going to get just as much scraped off as we go 6 meters per second. These are in meters per second to the right. So these two are going to be the same. So what it's really telling us, and we could say do it for 4 meters per second and -4, is it doesn't matter if we go to the left or the right. What really matters is the magnitude of the velocity or the absolute value of it, but it doesn't matter if we're going to the left or the right. Whether we're going to the left or the right for a given magnitude of velocity, we are going to get the same amount scraped off. Now let's see which of these choices are consistent with what I just said. Moving the sandpaper faster scrapes off more wood. Well, that's true. We see as the speed increases, or the magnitude of the speed increases, we scrape off more wood. As the magnitude of the speed, this -8, you might say, hey, that's lower than -2, but the magnitude is larger. We're going 8 meters per second to the left, and we're scraping off more. So this is a true statement, but it's not the significance of the evenness of the function. This could have been true even if this was a 7, but then this function would no longer be even. The piece of wood is 6 millimeters thick. Well, this doesn't really, we actually don't get any of that from the function. Moving the sandpaper to the right has the same effect as moving it to the left. Well, that seems pretty close to what I had said earlier, that for a given speed to the right or to the left, we get the same amount that is taken off of the piece of sandpaper or the piece of wood. So this looks like our answer. Keeping the sandpaper still doesn't scrape off any wood. Well, that is true, but once again is not the significance of the evenness of this function.
Manipulating formulas.
We are told that the formula for finding the perimeter of a
Formula.
rectangle is P is equal to 2L plus 2W, where P is the perimeter, L is the length, and W is the width. And just to visualize what they're saying, and you might already be familiar with this, let me draw a rectangle. And that looks like a rectangle. And if this side's length is L, then this side's length is also going to be L. And if this width is W, then this width up here is W. And the perimeter is just what is the distance if you were to go around this rectangle. And so that distance is going to be this W plus this L plus this W, or that width, plus this length. And if you have one W and you add it to another W, that's going to give you two W's. So that's two W's. And then if you have one L and then you have another L, that's going to give you, if you add them together, that's going to give you two L's. So the perimeter is going to be two L's plus two W's. They just wrote it in a different order than the way I wrote it. But the same thing. So hopefully that makes sense. Now, their question is, rewrite the formula so that it solves for width. So it solves for width. So the formula, the way it's written now, it says P is equal to something. They want us to write it so it's this W right here. They want it to be W is equal to a bunch of stuff with L's and P's in it and maybe some numbers there. So let's think about how we can do this. So they tell us that P is equal to 2 times L plus 2 times W. We want to solve for W. Well, a good starting point might be to get rid of the L on this side of the equation. And to get rid of it on that side of the equation, we could subtract the 2L from both sides of the equation. So let's do it this way. So you subtract 2L over here minus 2L. You're also going to have to do that on the left-hand side. So you're going to have minus 2L. We're doing it on both sides of the equation. Remember, an equation says P is equal to that. So if you do anything to that, you have to do it to P. So if you subtract 2L from this, you're going to have to subtract 2L from P in order for the equality to...
Alright, I already know the answer of this stuff. It seems like it somehow go back to the early math level. It shouldn't be very hard. Rewrite the formula so that it solves for ways. Oh, you just had to, let's say, put the W in one side of that equation. That's all.
The formula for the area of a triangle is A is equal to 1/2 B times H, where A is equal to area, B is equal to length of the base, and H is equal to the length of the height. So area is equal to 1/2 times the length of the base times the length of the height. Solve this formula for the height. So just to visualize this a little bit, let me draw a triangle here. Let me draw a triangle just so we know what B and H are. B would be the length of the base. So this distance right over here is B. And then this distance right here is our height. That is the height of the triangle. Let me do that in lowercase h because that's how we wrote it in the formula. Now they want us to solve this formula for the height. So the formula is area is equal to 1/2 base times height. And we want to solve for h. We essentially want to isolate the h on one side of the equation. It's already on the right-hand side. So let's get rid of everything else on the right-hand side. So we could do it, well, I'll do it one step at a time. We could kind of skip steps if we wanted to. But let's see if we can get rid of this 1/2. So the best way to get rid of a 1/2, and it's being multiplied by h, is if we multiply both sides of the equation by its reciprocal. If we multiply both sides of the equation by 2/1 or by 2. So let's do that. So let's multiply. Remember, anything you do to one side of the equation, you also have to do to the other side of the equation. Now, what did this do? Well, the whole point behind multiplying by 2 is 2 times 1/2 is 1. So on the right-hand side of the equation, we're just going to have a BH. And on the left-hand side of the equation, we have a 2a. And we're almost there. We have a b multiplying by an h. If we want to just isolate the h, we could divide both sides of this equation by b. We're just dividing both sides. You can almost view b as the coefficient on the h. We're just dividing both sides by b. And then what do we get? Well, the right-hand side, the b's cancel out. And the left-hand side, we're just left with 2a over b. So we get h and I'm just swapping the sides here, h is equal to 2a over b. 2a over b. And we're done. We have solved this formula for the height. And I guess this could be useful if
Alright, it's still quite simple. And I guess the three videos are just talking about the same thing, which is how can you manipulating the formula or especially the equation. Modeling with two variables. Let's get into it.
We're told that Chloe takes a slice of pizza out of the freezer and leaves it on the counter to defrost. She models the relationship between the temperature P of the pizza, this seems like it's going to be interesting, the temperature P of the pizza in degrees Celsius, and time T since she took it out of the freezer in minutes, as P is equal to 20 minus 25 times 0.8 to the T power. So that's how she's modeling her temperature of the pizza, P, as a function of time. She wants to graph the relationship over the first 25 minutes. So what we're going to do here is not so much focus on the graph itself, although we will look at that. I'm actually just going to use a graphing calculator in order to have access to the graph. But I want to look at the graph in the context of what we are trying to model and carefully think about what should be the labels for the axes, what parts of the graph are interesting. So this right over here is this function graphed on Desmos. You can see I typed it in right over here. P is equal to 20 minus 25 times 0.8 to the T power. Exactly what we had down here. Now, remember, this is modeling the temperature of our pizza as a function of time. So to help us remember that, let's put in some labels for our axes. So to graph settings, if I go down here, our x-axis. Now our x-axis is really the t-axis. That's our independent variable over here. And what is it measuring? Well, it says it right over here. It's measuring time t in minutes. So we could write it like this. T, which is measured in minutes. And then what about our y-axis? Well, this is really our p-axis, and that's measuring degrees Celsius. So that's our p-axis, and it's measuring degrees Celsius. All right, so let's just look at what our graph looks like so far. So there we have it. We put in our axes, and we have already typed this part in so I can make it so I can focus on the graph itself. Now, are we done?
Okay, so I guess this is just a basic level of mathematics. Any one of you, if you have ever going through the high school education level, then you would know the labels for the graph, you know. So that makes sense. Let's get into the next one. Rational equation word problem.
Dominique from Dominique's Pizza bakes the same amount of pizza every day. She used to spend $8 each day on using the oven and $1.50 on ingredients for each pizza. So $8 each day on using the oven and $1.50 on ingredients for each pizza. One day the price for the ingredients increased from $1.50 to $2 per pizza. Dominique made some calculations and found that she should bake 8 pizzas more each day. So the expenses for a single pizza would remain the same. And assume they're saying the total expenses for a single pizza, because clearly the ingredients cost is not the same. We're talking about the total ingredients. So if we were to spread the cost of the oven across all of the pizzas, write an equation to find how, or the total cost for the oven per day, to spread that across all the pizzas. Write an equation to find out how many pizzas Dominique baked each day before the change in price. Use P to represent the number of pizzas. So let's just think about her total cost per pizza before and then her total cost per pizza after if she bakes 8 more pizzas. So before, we're going to use P to say that's the number of pizzas she baked per day before the change in price. So before the change in price, on a given day, she would spend $8 on the oven and then $1.50 on ingredients for each pizza. So 1.5 or $1.50 times the number of pizzas. This would be her total cost on all the pizzas in that day. It's the oven cost plus it's the ingredients cost. So if you wanted this on a per pizza basis, you would just divide by the number of pizzas. Now let's think about what happens after the change in price. After the change in price, her cost per day for the oven is still $8, but now she has to spend $2 per pizza on ingredients, so $2 per pizza. And instead of saying that she's baking P pizzas, let's say that she's now baking 8 more pizzas each day. So it's going to be P plus 8. And so this is going to be her total cost for all of the pizzas she's she's now baking. And so if you want it on a per pizza basis, she's now making P plus 8 pizzas, you would divide by P plus 8. And the problem tells us that these two things are equivalent. Here you had a higher cost in ingredients per pizzas, but since you are now baking more pizzas, you're spreading the oven cost amongst more and more pizzas. So let's think about what P has to be. P has to be some number of pizzas so that these two expressions are equal. Her total cost per pizza before, when she only made P, is going to be the same as her total cost per pizza when she's making P plus 8 pizzas. So these two things need to be equal. So we did that first part, or we did what they asked us. We wrote an equation to find out how many pizzas Dominique baked each day before the change in price, and we used P to represent the number of pizzas. But now for fun, let's actually just solve for P. So let's just simplify things a little bit. Actually, so this part right over here, actually let's just cross multiply this on both sides. Or another way of thinking it is multiply both sides times P plus 8 and multiply both sides times P. So if we multiply by P plus 8 and we multiply by P, we multiply by P plus 8 and we multiply by P, that cancels with that cancels with that. On the left hand side, so let's see, we have to just do the distributive property twice right over here. What is P times 8 plus 1.5P? Well, that's going to be 8P, I'm just multiplying the P times this stuff first, plus 1.5P squared. And now let's multiply the 8.
Alright, so the calculation part for this is quite simple. I guess every one of you knows that, so we don't cover that here. Let's get into the third video.
Lisa owns a random candy vending machine, which is a machine that picks a candy out of an assortment in a random fashion. Lisa controls the probability in which each candy is picked. She is running out of Honey Bunny, so she wants to program its probability so that the probability of getting a different candy twice in a row is greater than 2 1/4 times the probability of getting Honey Bunny in one try. So let me read that again. She wants to program its probability so that the probability of getting a different candy twice in a row, or really any other candy twice in a row, is greater than 2 1/4 times the probability of getting Honey Bunny in one try. Write an inequality that models the situation. Use P to represent the probability of getting Honey Bunny in one try. Solve the inequality and complete the sentence. Remember that the probability must be a number between 0 and 1. So we want to write the inequality that models the problem here, and then we want to complete the sentence. The probability of getting Honey Bunny in one try must be, so they give us a bunch of options, greater than or equal to, less than or equal to, and then we have to put some number here. So to work through this, I've copy and pasted this problem onto my little scratch pad right over here. And so let's just think about it a little bit. So they tell us use P to represent the probability of getting Honey Bunny in one try. And they also say she wants to program its probability so that the probability of getting a different candy twice in a row is greater than 2 1/4 the probability of getting Honey Bunny in one try. So if P is the probability of getting Honey Bunny, what's the probability of getting any other candy at once? Well, that's going to be 1 minus P. If you have a probability of P of getting Honey Bunny, well, then it's 1 minus P of anything but Honey Bunny. Now, what's the probability of getting this twice in a row?
Okay, I just lost my mind a few minutes ago, so let's get into it again and try to understand what's going on there. So it says that Lisa, this is a person, owns a written candy vending machine, which is a machine that picks a candy out of an assortment in a written fashion. Lisa controls the probability in which each candy is picked. She's running out of Honey Bunny, so she wants to program its probability so the probability of getting a different candy twice in a row is greater than that number times the probability of getting Honey Bunny in one try. Write an inequality that models the situation. Use P to represent the probability of getting Honey Bunny in one try. So the Honey Bunny is probably a brand for a candy or for a candy. So yeah, this could be a little bit hard since I have no idea how to do that.
Lisa controls the probability in which each candy is picked. She is running out of honey bunny, so she wants to program its probabilities so that the probability of getting a different candy twice in a row is greater than 2 1/4 times the probability of getting honey bunny in one try. So let me read that again. She wants to program its probabilities so that the probability of getting a different candy twice in a row, or really any other candy twice in a row, is greater than 2 1/4 times the probability of getting honey bunny in one try. Write an inequality that models the situation. Use P to represent the probability of getting honey bunny in one try. Solve the inequality and complete the sentence. Remember that the probability must be a number between 0 and 1. So we want to write the inequality that models the problem here, and then we want to complete the sentence. The probability of getting honey bunny in one try must be, so they give us a bunch of options, greater than or equal to, less than or equal to, and then we have to put some number here. So to work through this, I've copy and pasted this problem onto my little scratch pad right over here. And so let's just think about it a little bit. So they tell us use P to represent the probability of getting honey bunny in one try. And they also say she wants to program its probability so that the probability of getting a different candy twice in a row is greater than 2 1/4 the probability of getting honey bunny in one try. So what's, if P is the probability of getting honey bunny, P is the probability of getting honey bunny, what's the probability of getting any other candy at once? Well, that's going to be 1 minus P. If you have a probability of P of getting honey bunny, well, then it's 1 minus P of anything but honey bunny. Now, what's the probability of getting this twice in a row, of getting anything else twice in a row? Well, you're just going to multiply this probability times itself. It's going to be 1 minus P times 1 minus P, or we could just write that as 1 minus P squared. So this right over here is the probability of getting a different candy, any other candy, twice in a row. So prob of any other non-honey bunny candy, any other candy, twice in a row. Now they tell us that this needs to be greater than, this probability needs to be greater than 2 1/4 times the probability, 2 1/4 the probability of getting honey bunny in one try. So is greater than 2 1/4 times the probability of getting honey bunny in one try. Well, that is P times P. So we have just set up the first part. We have written an inequality that models the situation. Now let's actually solve this inequality. And so to do that, I will just expand 1 minus P squared out. 1 minus P squared is the same thing as P squared, well, I'll just multiply it out. So this is going to be 1 squared minus 2P plus P squared, and that's going to be greater than 2 1/4 P, greater than 2 1/4 P. Now let's see, if we subtract 2 1/4 P from both sides, we're going to be left with, and I'm going to reorder this, we're going to get P squared. So you have minus 2P minus 2 1/4 P. So that's going to get us minus 4 1/4 P. Or let me just write that as 17 over 4P plus 1. Plus 1 is greater than 0. Is greater than 0. And so let's think about solving this quadratic right over here. And under which circumstances is this greater than 0? And to think about it, let's factor it. And actually, before we factor it, let's simplify it a little bit. I don't like having this 17/4 right over here. So let's multiply both sides times 4. And since 4 is a positive number, it's not going to change the sign of the direction of this inequality. So we could rewrite this as 4P squared minus 17P plus 4 is greater than 0. Is greater than 0. And let's see, what are the roots of this? And we could use the quadratic formula if we wanted to do it really quick. We could probably do it other ways. But negative b, so it's going to be 17 plus or minus the square root of 17, negative 17 squared, b squared, so that's 289, minus 4 times a times c. Well, a times c is 16 times 4, so minus 64. All of that over 2 times a. All of that over 8, so that's 17 plus or minus, let's see, this is the square root of 225 over 8, which is equal to 17 plus or minus 15 over 8, which is equal equal to, let's see, 17 minus 15 over 8 is 2/8, which is equal to 2/8 or 1/4. So that's one of them. That's when we take the minus. And if we add 17 plus 15, that gets us to 32 divided by 8 is 4, or 4. So there's two situations right over here. So we could, let's factor this out. We could write this as p minus 1/4 times p minus 4 is greater than 0. So under what circumstances is this going to be true? What constraints are this going to be true? Well, if you're taking the product of two terms and they are going to be greater than 0, that means that these two things have to be the same sign. Or actually, in particular, they both have to be positive or they both have to be negative. So let's look at those two situations. So I'll switch colors here just for fun. So both positive or both negative. So if they're both positive, that means that p minus 1/4 has to be greater than 0, and p minus 4 is greater than 0. Add 1/4 on both sides right over here. You get p is greater than 1/4, and p is greater than 4. So that's the situation where they are both positive. Now, what about if they're both negative? Well, then you have p minus 1/4 is less than 0, and p minus 4 is less than 0. Add 1/4 here. So p needs to be less than 1/4, and p needs to be less than 4. Now,
Alright, so from this graph, at least we learn a new stuff. How can we solve the inequality like this one? Well, we just have to find out the both situations where the both expression is positive or negative. This is for the greater than 0 situation. If the whole expression is less than 0, then that means one of them must be positive, another one must be a negative. Then we still could be able to write out two situations where we can do some calculations.
Now, what does this constraint simplify to? P has to be greater than 1/4 and p has to be greater than 4. Well, if p is greater than 4, it's definitely going to be greater than 1/4. So all of this collapses into p needs to be greater than 4. That's the situation where both are positive. P must be greater than 4. Now what about here? Well, if p is less than 1/4, it's definitely going to be less than 4. And this is an and right over here. So this collapses to p is less than 1/4. So which one do we go with? P needs to be greater than 4 or p needs to be less than 1/4? Well, we need to remind ourselves that we're talking about a probability. To go back to the original problem, we're talking about a probability of someone getting honey bunny in one try. A probability must be between 0 and 1. So the probability having to be greater than 4, well, that just doesn't make any sense. That doesn't make any sense in the context of this question. So we have to go with the probability of getting honey bunny needs to be less than 1/4 or less than 0.25, which...
Okay, let's get into the next one, exponential equation word problem.
Liam opened a savings account and put $6,250 in it. Each year, the account increases by 20%. How many years will it take the account to reach $12,960? Write an equation that models the situation. Use t to represent the number of years since Liam opened the account. So I encourage you to pause this video and actually try to do it on your own first. Try to write this equation that models the situation using the t, variable t in the way they described, and then actually answer the question. How many years will it take for the account to reach $12,960? Well, let's just think about it. So t is to represent the number of years since Liam opened the account. So let's just say it's been 0 years since Liam opened the account. How much is he going to have? Well, he's just going to have $6,250 in it. That's how much he starts with. Now let's say it's been 1 year. 1 year since he opened the account. How much will he have? Well, he's going to have $6,250 times, or let's write it this way, plus 20% of $6,250. It grows 20% every year. So this is how much he started the year with, and then he gets another 20% of that $6,250. If we factor out a $6,250, this is equal to $6,250 times 1 plus 20%, or we could write that as 0.2, which is equal to 6,250 times 1.2 times 1.2. Now, how much is he going to have at the end of 2 years? Well, he's going to have the same amount that he had at the end of 1 year times 1.2, because it grew by 20% again. So he's going to have the amount that he had at the end of 1 year times 1.2 times 1.2, which is equal to 6,250 times 1.2 times 1.2 times 1.2 times 1.2, which is equal to 6,250 times 1.2 squared. 1.2 squared. I think you might see where this is going. Or I could even write it like this. Order of operations, you do the exponent first. So what about after 3 years? So after 3 years, well, we're just going to compound. We're going to multiply by 1.2 once again. So then he's going to have 6,250 times 1.2 to the third power. And so after t years, we're going to multiply by 1.2 that many times. So after t years in his account, he's going to have 6,250 times 1.2 to the tth power. 1.2 to the tth power, or to the t power. I don't want to get confused with a part of your, or I guess the thing that you use to take bytes with. Anyway, so they say write an equation that models the situation. So we want to figure out how many years will it take the account to reach 12,960. So we essentially want to say, when is the account going to be 12,960? So, or we could write 12,960. When is that going to be equal to 6,250 times 1.2 to the t power? So that's the equation right over there that models the situation. And then we need to think about how we can actually go about solving this thing. Well, a natural thing is to isolate the t variable. Let's divide both sides by 6,250. So we could get, and if we flip the two sides, we could get 1.2 to the t power is equal to 1,200, or let me write this, 12,960 divided by 6,250, 6,250. And since they're both divisible by 10, why don't we divide them both by 10? So it's 1,296 divided by 625. And there's several ways that you could solve this problem at this point. One way, if you feel confident that this is going to have an integer answer right over here, you could literally just try to use your calculator and multiply 1.2 enough times to get whatever number this is. And so we could do it that way. And as we'll see, there's a more systematic way of doing it once you learn about logarithms. And I'll do that at the end, but I'll do that last just in case you haven't been exposed to logarithms yet. So you could literally say, so let me just exit out of everything. So you could literally say, okay, let's see, 1296 divided by 625 is this value. So let's see how many times we have to multiply by 1.2. 1.2 times 1.2 gets us, well, that doesn't get us close enough. So let's try it 3 times. So let's take that same number. Let's just take 1.2. Let's raise 1.2. Let's just do it 3 times 1.2 times 1.2. That still doesn't get us there. What if we were to multiply by 1.2 one more time? Well, that actually gets us there. So you see, if you and we just did this by brute force. 1.2 to the 4th power will give us this value. So that's one way, kind of a brute force way of figuring out that t is equal to 4. Another way, and this might be a little bit less intuitive, it might jump out of it. Gee, this looks like some type of a power of 5. We know that 5 to the first is 5. 5 squared is 25. 5 to the third is 125. 5 to the fourth is 625. And so you might recognize this right over here is 5 to the fourth. And it's actually a little bit harder to recognize that this right over here is 6 to the 4th power. And this right over here is 6/5. So we could rewrite this as 6 over 5 to the t is equal to 6 to the 4th over 5 to the 4th, which is the same thing as 6 over 5 to the 4th power. So here you'd say,
okay, I thought he will convert the whole equation into some equation that contains the logging, the log, and then use a calculator to solve out the problem. But in the end, he did something. Oh, here we go, the log.
if you say, look, Let's take the thing that we want 1.2 to some power to be. Let's take the logarithm of that. And actually, you could take a logarithm any base. Your calculator tends to have a natural log, which is base e, and a log base 10. We could just take log base 10. So let's do that. So we'll take the logarithm of what we want to get to, 2.0736, and divide that by the thing that we're trying to take the power of to get to this number. So divided by the logarithm of 1.2. And once again, we prove this. Actually, I wanted to divide. So let me insert a division symbol. So once again, it might look like a little voodoo right here. We prove it in other videos, but if you wanted to use the calculator to calculate things like this, because sometimes it won't be a nice integer number of years. It might be 3.5 years, or it might be 7.1234 years, whatever it might be. This will give you a more precise answer. So what do you want to get to? You want to get to 2.0736. What are you raising to some power? 1.2. Divide the log of the thing you're trying to get to, divided by the log of what you're taking, what the base that you're trying to raise to a power, and you click enter, and then you get. So this is literally another way of saying that 1.2.
Okay, the last section is modeling with beautiful variables.
We are told that Jade is making pancakes using flour, eggs, and milk. This table gives the cost per kilogram of each ingredient and the amount in kilograms that Jade uses. All right. The total amount Jade spends on ingredients is $6. Write an equation that relates A, B, C, and D. Pause this video and see if you can have a go at this. All right, now let's go through this together. So I like to do these in real time so that you can see my thought process. So I'm here with you right now. So let's see. The total Jade spends, and this is going to be on flour, eggs, and milk, is going to be $6. So one way to think about it is and I'll do this in different colors, the flour dollars plus the eggs dollars, or the amount that Jade's going to spend on eggs, plus the amount that Jade spends on milk, I'll call that the milk dollars, is going to be equal to the total amount, is going to be equal to $6. And so what's the total amount that Jade is going to spend on flour? Well, we can just look right over here, $0.9 per kilogram times A kilograms. So Jade is going to spend 0.9 A dollars. I'm just going to multiply these two things to figure out how much Jade spends on flour. And so this is going to be equal to, and I'll lose the dollar symbol just so we can focus on the numbers and the variables, 0.9A. 0.9A. And this is, of course, is going to be in dollars, which is important. I'm going to add dollars plus dollars plus dollars to get dollars. Now, what about eggs? Well, the same notion. 0.2 kilograms times B dollars per kilogram. If I take the product of these two, I'm going to get 0.2 B dollars. Or I could just think of it as 0.2 B if I don't write the dollar symbol. And then last but not least, on milk, let me look at the product of these two things, of this and of this. So D kilograms at C dollars per kilogram. That's just going to be CD dollars. So plus CD. And all of that is going to be equal to $6. And we're done. We wrote an equation that relates A, B, C, and D.
This is simple. All right, so how about we just get into the last one, because I don't want to waste that much time on this.
We're told that given the height h and volume v of a certain cylinder, Jill uses the formula r is equal to the square root of v over pi h to compute its radius to be 20 meters. If a second cylinder has the same volume of the first, but is 100 times taller, what is its radius? Pause this video and see if you can figure this out on your own. All right, now let's do this together. So first, I always like to approach things intuitively. So let's say the first cylinder looks something like this. And then the second cylinder, here it's 100 times taller. I would have trouble drawing something that's 100 times taller. But if it has the same volume, it's going to have to be a lot thinner. So if you want to maintain the volume, as you make the cylinder taller, and I'm not going anywhere close to 100 times as tall here, you're going to have to decrease the radius. So we would expect a radius to be a good bit less than 20 meters. So that's just the first intuition, just to make sure that we somehow don't get some number that's larger than 20 meters. But how do we figure out what that could be? Well, now we can go back to the formula. And we know that Jill calculated that 20 meters is the radius. So 20 is equal to the square root of v over pi h. And if this formula looks unfamiliar to you, just remember the volume of a cylinder is the area of one of the either the top or the bottom. So pi r squared times the height. And if you were to just solve this for r, you would have this exact formula that Jill uses. So this isn't some new formula. This is probably something that you have seen already. So we know that 20 meters is equal to this. And now we're talking about a situation where we're a height that is 100 times taller. So this other cylinder is going to have a radius of square root of, v is going to be the same. So let's just write that v there. Pi doesn't change. It's always going to be pi. And now instead of h, we have something that is 100 times taller. So we could write that as 100h. And then what's another way to write this? Well, what I'm going to do is try to bring out the 100 so I still get the square root of v over pi h. So I could rewrite this as the square root of 1 over 100 times v over pi h, which I could write as the square root of 1 over 100, and I'm just using properties of radicals here, times the square root of v over pi h. Now we know what the square root of v over pi h is. We know that that is 20, and our units are meters. So this is 20. And then what's the square root of 1 over 100? Well, this is the same thing as 1 over the square root of 100. And of course now it's going to be times 20. Times 20. Well, the square root of 100, I should say the principal root of 100, is 10. So the radius of our new cylinder, of the second cylinder, is going to be 1/10 of 20, which is equal to 2 meters. And
okay, so actually I don't know that if we could do this thing before. I don't know that. Okay, it seems like we got an expression. We got an expression under the square root, and that expression was composed by two fractions where they multiply each other. Then we could separate it into two square root expressions, something like that, and the value won't change. Okay, basically we just finished all the learning for the Algebra 2. Congratulations, guys. That means we could get into the next part, which is pre-calculus and AP statistics. And after this part, we will get into the high level of mathematics. We are going to learn the calculus. But don't let's say before that, we still had to learn this part, pre-calculus and AP statistics. No problem, we could do that. So basically this is today's learning, and I'll see you guys in the next video. Bye.